r dot square. For a constant m, let's get it for a constant m. So I have r dot square. Let's differentiate it with respect to itself, r dot. So you get 2 r dot, right? To cancel with the half, you have m r dot times the derivative r dot, right? Which is r double dot. Again, it's like 1/2 mv squared. This quantity is function of velocity, so let's differentiate it with respect to velocity first. So you get 2v times the derivative of velocity. It's a chain rule. The derivative of velocity is acceleration. That's r double dot. Do it in terms of v or in terms of r dot. It's up to you. Any problem with this? That this is the time rate of change of this term? Any question here, please? Have a question, come up with it. Yeah, I know that I'm pushing you away from the course, but this has nothing to do with the fact that if you have any question, you need to come up with it. It's 1/2 mv squared, and I want to differentiate this with respect to time. This is not straightforward a function of time. This is not explicit function of time. So you need to do the chain rule. Differentiate with respect to velocity, because it's a function of velocity. Time is dv by dt, right? This is easy. This is simply mv or mr dot. And dv by dt, this is the acceleration. So this is v dot or r double dot, right? So this is what is here. Any question? We'll do a lot of chain rules in that course. All differentiations simply are with respect to time, but we're differentiating quantities that are not explicit functions of time. This is all over the course we're going to do the same thing. The dot product is, we can just swap things together. So I can do this, right? And I think you can guess why now, because mr dot is what? Yeah, this is Newton's second law. So I'm using Newton's second law here. Okay, so let's do integration for both sides. Oh. Integration from this guy between 2 times t1 and t2. Integration this guy between t1 and t2. Okay. So I'm going to multiply also even before the integration. Let's write it in a new line. So dt is f dot r dot dt, which is, what is r dot dt? What is r dot first? What's r dot? It's dr by dt times dt, so you get what? Yeah, so this is f dot dr. And now I'm going to integrate between the two limits, the initial and final point that I have. This is between the point 1 and point 2. This is between the point 1 and point 2. So integration of dt is just t between two limits. So it's t2 minus t1, the change in kinetic energy, equals, what is this quantity by definition? We're defining a new quantity, and for sure you have seen it before. What is this quantity? Anybody remembers? Work. Exactly. It's the work done by all the applied force. So we're defining this now, and I am giving this rule now. What's the rule that we got? Is that the change in kinetic energy is simply equal to the work done by the applied loads. And please, this is a generic rule. It is always the case. There is a misconception coming from undergrad that this is applicable only to conservative forces. I did not specify or assume whatsoever that the forces are conserved. I didn't say anything about the nature of the forces. Okay? So this is always true. As long as Newton's second law is true. Okay? Because we used it in the derivation. The change in kinetic energy is equal to the work done by all the applied loads. If you have a friction, if you have a non-conservative load, this is applicable. Okay? Any question about that? Any question? Okay. Some time to write. Use the other board to define conservative forces afterwards. So the main basic quantity of Newtonian mechanics is a vector quantity called the linear momentum. Its evolution is dictated or governed by Newton's second law. The main basic quantity in Lagrangian mechanics, we're going to introduce it later, is actually the kinetic energy. The main governing law is the change in kinetic energy is equal to the work done. This is equivalent to Newton's second law, but it's just a scalar version of it, so it's not complete because it gives you just a single equation. Over there, Newton's second law is a vectorial equation. You can get 3 equations out of it, right? For each part. Okay, let's now define what do you mean by conservative forces. Conservative forces and potential energy. It's in relation to potential energy. Okay. First of all, the naming conservative is not confined to dynamics. I'm going to define here a conservative vector. So this is pretty generic in mathematics. A conservative vector A is such that A can be written, A is a vector, okay? Can be written as the gradient of a scalar function phi. Anybody doesn't know the gradient? Should be taking it in 200A, NAE. Simply partial x of the quantity in the I direction, partial y in the j direction, partial z in the k direction. Okay? Which means that the x component of this vector is simply determined by differentiating this function with respect to x. If you want the y component, differentiate this function with respect to y. If you want the z component, differentiate with respect to z. If you want the component in the r direction, differentiate with respect to r. Okay? So this is what we mean that a vector is determined by the gradient of a scalar function. If you have a vector of this type, we'll call it a conservative vector. This concept is general in mathematics. Okay? Okay. What do these vectors have as properties? Is that the line integral of this vector now, if you do it with respect to dr, if you do the line integral between 2 points, okay, this is equal to, by definition, since it's a conservative vector, I'm going to replace A by the gradient of the scalar function. And what is the gradient of phi? It's simply d phi by dr, right? This is the definition. So d phi by dr dotted with dr, what do you get out of that? What do you get? d phi. So this is simply the integration of d phi between 2 limits. And what is the integration of d phi between 2 limits? Yes, the integration of any d something is the something, right? d phi is phi between 2 limits, so it's phi 2 minus phi 1. This is the change of this scalar function, which means that if you have here 0.1 and 0.2, and you're going between 0.1 and 0.2, there are maybe infinitely many paths to go between 0.1 and 0.2. And in general, if you are integrating, if you're adding, accumulating some vector along this path, this accumulated quantity in general should be different if you add it along that path and different from the quantity that you get it if you add it along that path, correct? This is in general. But if the vector is conservative, if the vector is a conservative vector, the line integral of A along any line is simply what? Phi and the final point minus phi of the initial point has nothing to do with the path. So the line integral of a conservative vector is path independent. Okay? This is an important property. Line integral is path independent. Any question about that? Any question? Please, if you have a question, come up with it. I promise you that most of you will get out knowing nothing. So if you come up with questions, you do a benefit to your colleagues, right? Because I will explain more. Please, any question? Okay, this is in general, up to this point, this was actually maybe a part of lecture in mathematics. Now we're gonna confine it to dynamics. We're gonna project this knowledge to dynamics.